Welcome to TV Part 3, Audio. In this video, you will examine the steps necessary for the audio reproduction in a typical color television receiver. You will start with the IF sound carrier outputted by the mixer stage and follow it through the necessary stages to arrive at the speaker system. The stages we will examine are the first, second, and third video IF amplifier stages, the sound IF detector stage, the sound IF amplifier stage, the sound detector stage, and finally, the audio amplifier stage. The sound IF detector stage, sound IF amplifier stage, sound detector stage, and the audio amplifier stage are all a part of what is known as the sound strip. As you may recall from TV Part 2, the mixer stage outputs an intermediate sound carrier at 41.25 MHz. This down-converted signal contains the frequency modulation necessary for audio reproduction in the color television receiver. Now let's examine this signal to understand exactly what it is. When the mixer stage heterodyned the sound carrier with the local oscillator signal, a new intermediate sound carrier was generated which contained the same modulation but with a lower carrier frequency. The sound IF carrier is capable of deviating plus and minus 25 kHz from its center or resting frequency. This amount of deviation allows an audio frequency range from 50 Hz to 15,000 Hz to be conveyed to the television sound system. Generally, a television program will not make full use of this sound range. Now that you understand more about the intermediate sound carrier, let's follow it through the stages within the television receiver and see how it becomes live sound. The intermediate sound carrier leaves the mixer stage and is connected to the first video IF amplifier stage by a coax cable, usually 50 or 75 ohms. Here you see the first video IF amplifier stage the intermediate sound carrier must pass through. Only a very small portion of the IF sound carrier will get amplified compared to the amplification of other frequencies this amplifier handles. The 41.25 MHz IF sound carrier is capacitively coupled into the first video IF amplifier stage by a tuned capacitor C2. The sound carrier passes through the primary winding of transformer T1. The tank circuit, composed of inductor L1 and capacitor C4, is tuned to the IF sound carrier of 41.25 MHz. As you may recall, a tank circuit will use up or dissipate any energy at its tuned resonant frequency when placed in series with that circuit. It now becomes apparent that this tank circuit is a frequency trap which partially attenuates the IF sound carrier. Capacitor C3 determines how much intermediate sound carrier is coupled to the below trap circuit. After the IF sound carrier is attenuated, the rest of it passes through the secondary of transformer T1. Capacitor C6 couples the intermediate sound carrier into the base of transistor Q1. At this point, transistor Q1 amplifies everything it sees, including the reduced IF sound carrier. Now, the somewhat amplified IF sound carrier is coupled out of the first video IF amplifier stage by capacitor C9 and into the second video IF amplifier stage. The intermediate sound carrier is now coupled into the second video IF amplifier stage by capacitor C9. The IF sound carrier passes through resistor R5, which limits all input entering through the base of transistor Q2. Transistor Q2 provides second-stage amplification of any signal applied to it. The IF sound carrier passes out of the collector of transistor Q2 and into coupling capacitor C17. The intermediate sound carrier is coupled out of capacitor C17 and into the third video IF amplifier stage. Once the IF sound carrier is coupled into the third video IF amplifier stage, resistor R12 limits the signal passed to transistor Q3. Transistor Q3 provides the last step of video IF amplification to the intermediate sound carrier. The IF sound carrier is taken off the collector of transistor Q3 and passed into the sound strip of the television receiver. Up until now, we have followed the intermediate sound carrier through the first, second, and third video IF amplifier stages. With the majority of color television receivers, the video IF amplifier stages do not amplify the intermediate sound carrier to the extent of other signals present, yet the intermediate sound carrier is amplified to a certain degree. At this time, we will pause for a short review of the material just discussed. The intermediate sound carrier is produced by the heterodyning effect of the mixer stage. The IF sound carrier is a frequency-modulated signal containing the modulation of the original broadcast signal from the television station. The frequency deviation of the IF sound carrier is plus minus 25 kHz. This makes the overall bandwidth occupied by the intermediate sound carrier a total of 50 kHz. In the color television receiver, the IF sound carrier passes through the video IF section with a small degree of amplification. This concludes review number 1. At this time, stop the video and complete section A in your student workbook. Today's modern television receivers use a process called the intercarrier sound system. To understand the importance of this process, let's look at the main problem television receivers faced prior to the development of intercarrier sound. In the early days of television, a television receiver had to be fine-tuned to get the best picture and sound when going from channel to channel. Often compromises had to be made between picture quality and sound quality. This was because the mixer stage in the television receiver had two outputs, one output for the IF picture carrier and the other for the IF sound carrier. Likewise, each IF carrier had its own IF amplifier section. This method of amplification was known as the split sound IF system. When one or both of the IF amplifier sections would be out of adjustment, tuning problems would arise in picture or sound quality. The intercarrier sound system uses one mixer output and one main video IF amplifier section, as you have seen up to this point in the You Can Do television series. The intercarrier sound system uses the 4.5 MHz spacing between the IF sound carrier and the IF picture carrier as a standard frequency reference. The 4.5 MHz frequency is obtained through the process of heterodyning or mixing two signals together. These two signals are, of course, the IF sound carrier and the IF picture carrier. By using the higher amplitude IF picture carrier as the oscillator signal and the lower amplitude IF sound carrier as the RF signal to be downconverted, a new intermediate FM sound carrier is created. This new intermediate FM sound carrier will have a center or resting frequency of 4.5 MHz, the same as the distance between the sound carrier and the picture carrier. The 4.5 MHz standard does away with the problem of two independently tuned IF sections as used in the split sound IF system. The starting point of the intercarrier sound system in a television receiver is known as the sound takeoff. In a color television receiver, the sound takeoff is a connection after the second or third video IF amplifier stage. At this point, the IF sound and picture carriers are sampled. Now let's examine the stage responsible for heterodyning the IF sound carrier with the IF picture carrier to produce the new 4.5 MHz IF signal. The first stage in the color television sound strip is the sound IF detector stage. Here you see the sound IF detector stage of a color television receiver which downconverts the 41.25 MHz IF sound carrier into the new frequency modulated 4.5 MHz intermediate signal. Capacitor C1 and inductor L1 form the series resonant circuit tuned to 40 MHz. The bandwidth is wide enough to pass both the 41.25 MHz IF sound carrier and the 45.75 MHz IF picture carrier. This series resonant circuit is the link between the video IF amplifier stage and the beginning of the sound takeoff. In a color television receiver, the sound takeoff would be the connection between capacitor C1 and inductor L1. Diode D1 is known as a heterodyne detector and functions as the medium to mix the IF sound carrier with the IF picture carrier. The result is the new 4.5 MHz signal. A large difference in amplitude levels is required to pass the FM characteristic of the 41.25 MHz IF sound carrier to the new 4.5 MHz signal. The level of the IF sound carrier must be 2 to 5% of the IF picture carrier in order for proper heterodyning to take place. Resistor R3 is the diode load resistor for the sound IF detector stage. Capacitor C4 is an IF filtering capacitor which works in conjunction with resistor R3. Inductor L2 considerably reduces or dampens the higher frequency video signals which may be coupled into this stage. These unwanted video signals can be passed by series diode D1 when a higher than normal reverse bias capacitance across its PN junction occurs. Simply stated, inductor L2 acts as a high-frequency choke. Capacitor C5 and inductor L3 form a series resonant circuit tuned to a center frequency of 4.5 MHz. This series resonant circuit ensures the passage of the 4.5 MHz sound signal while rejecting any remaining composite video. As you can see, the sound IF detector is quite a simple circuit. At this point, we will pause for a review of the material just discussed. The intercarrier sound system is the solution to compromising picture quality and sound quality. The intercarrier sound system makes use of the 45.75 MHz IF picture carrier and uses it as the oscillator signal to heterodyne the 41.25 MHz IF sound carrier. The IF sound carrier must be 2 to 5% of the IF picture carrier for the FM characteristic to be passed on to the new 4.5 MHz signal. A tuned series resonant circuit is used to link the video IF amplifier stage to the beginning of the sound takeoff. Within the sound IF detector stage of a color television receiver is one main component called the heterodyne detector. This diode mixes the IF sound carrier with the IF picture carrier to obtain the new frequency-modulated 4.5 MHz signal. This concludes review number 2. Now stop the video and complete section B in your student workbook. Here you see the sound IF amplifier stage. The purpose of the sound IF amplifier stage is to substantially increase the power level of the 4.5 MHz signal. This increase is necessary for the next stage to have sufficient signal strength to function properly. In some television receivers, a limiter function may also be included in the sound IF amplifier stage. Bear in mind that a distortion-free FM signal requires that the FM carrier must remain constant in amplitude. This limiting function can be achieved by a single transistor located just before the output of the sound IF amplifier stage. The clipping process is achieved by biasing the transistor's base lower than normal so that the top of the FM waveform is clipped. Now let's examine the sound IF amplifier stage to see how it operates. Here you see a dual limiter amplifier circuit. Each transistor stage not only limits the 4.5 MHz signal, but amplifies it as well. The 4.5 MHz signal, which comes from the sound IF detector stage, is impedance matched into the sound IF amplifier by capacitors C6 and C7. A correct impedance match is required to drive the base of transistor Q1. The capacitive reactance of capacitors C6 and C7 provides a voltage divider at 4.5 MHz, so the signal levels will be appropriate going into this stage. A correct impedance match also keeps the previous stages from being loaded down. Resistors R4 and R5 form a voltage divider to supply transistor Q2's emitter with the correct DC voltage level. This voltage level biases transistor Q1's input to limit the positive half of the incoming waveform. Resistors R4 and R5, in conjunction with resistor R7, also provide negative feedback to transistor Q1. Capacitor C12 acts to regulate the negative feedback voltage. Diode D2 bridges across the emitter and base of transistor Q1. Diode D2 clamps the 4.5 MHz IF signal level going into the base. For this reason, the current across D2 is at times quite high. This diode serves to clip each negative half cycle of the input signal. Resistor R6 and capacitor C9 work together to regulate what transistor Q1's emitter sees. Resistor R6 provides the DC path, while capacitor C9 couples any AC signals to ground. Notice that both transistors Q1 and Q2 are configured into a direct coupled two-stage IF amplifier. Transistor Q1 functions to provide sufficient drive to transistor Q2. The circuitry in which transistor Q2 is placed is also a form of the Colpitts oscillator. The oscillator part of the circuit will be placed at the center frequency of 4.5 MHz. The limiter function of the circuit clips the amplitude levels to pass only the frequency modulation component of the signal. Notice the loop circuit, consisting of transistor Q2's collector, resistor R8, capacitor C13 and C14, and transistor Q2's emitter. When transistor Q2 is biased off, capacitor C13 and C14 charge. When transistor Q2 is biased on, capacitor C13 and C14 discharge through Q2 and resistor R8. An in-phase signal reference for the next stage is provided by the junction of capacitor C13 and C14. The primary of transformer T1 is used as the output of the circuit and is the means of coupling the output to the next stage in the television sound strip. Notice Zener diode D3 connected to the bottom of transformer T1's primary winding. Zener diode D3 is used to help maintain the RF amplitude level of the 4.5 MHz IF signal by acting to stabilize the voltage within the resonant circuit. Remember, in order to demodulate an FM signal, the amplitude levels of the modulated signal must remain constant, otherwise distortion results. As you can see, when transistor Q1 conducts, a lower voltage level appears at the base of transistor Q2, which biases Q2 off. Current rushes from ground and passes through resistors R5 and R7, bypassing transistor Q2 and charging capacitor C13 and C14. The current flows to the primary winding of transformer T1 and through resistor R11 tied to the positive potential. When transistor Q1 is no longer sinking current, a high voltage level is present at the base of transistor Q2 because of the pull-up resistor R9. Transistor Q2 will now act like a switch to discharge capacitor C13 and C14 through resistor R8, while at the same time creating a current change through transformer T1's primary winding. The change in T1's primary produces magnetic lines of flux which couple into its secondary winding. When the frequency deviates, the reactance of transformer T1 changes. Transformer T1 secondary provides the amplified IF signal to the next stage of the television sound system. At this time, we will pause for a short review of the material just discussed. The main purpose of the sound IF amplifier stage is to substantially increase the power level of the frequency-modulated 4.5 MHz signal, so the next stage will have sufficient signal strength to function properly. Signal limiting may be used in the sound IF amplifier stage to help eliminate distortion of the FM signal during the sound detection process. The limiting function is almost always accomplished in the last half of the sound IF amplifier stage, although in our example, limiting was accomplished in both halves of the stage. This concludes review number 3. Now stop the video and complete section C in your student workbook. The next stage within the sound strip of the color television receiver is the sound detector stage. The sound detector stage converts the 4.5 MHz frequency modulated intermediate signal into a low-level audio signal. Let's take a look at the theory in which this happens. The sound detector stage itself is a tuned resonant circuit. The frequency of this tuned circuit will be the center frequency of its input signal. In this case, the center frequency is exactly 4.5 MHz. The reactance of the sound detector circuit will change when the input signal swings or deviates from the circuit's tuned resonant frequency. When the reactance changes, the electrical balance of the circuit changes. With the electrical balance of the circuit changing, a low-level audio signal is reproduced. All of this happens because the 4.5 MHz signal is changing frequency according to the modulation contained in it. Now let's examine the most popular sound detector circuit used in color television receivers today. Here you see a ratio detector. You may recognize the ratio detector from YouCanDo's FM Radio Part 1 video, where this detector was explained quite thoroughly, along with other FM detectors. Although the basic circuit configuration is the same as found in a standard FM radio broadcast receiver, the frequency and operating bandwidth are different. This results in a different selection of component values used in the sound detector stage of the television receiver. The ratio detector, like other detector circuits, obtains its full power from the RF input signal. The ratio detector only conducts on 1/2 cycle of its tuned resonant frequency. For this reason, the ratio detector only has half the output of other detector circuits. However, the trade-off for reduced output is increased signal quality. Now, let's examine the ratio detector circuit. The ratio detector can be divided into two parts. The first part being the tuned tank circuit, consisting of T1 secondary winding and capacitors C16 and C17. The function of this half of the circuit is to maintain tuning at exactly 4.5 MHz. Any change of the input signal from this frequency will naturally change the reactance of the circuit. The tuned tank circuit is the heart of any FM detector circuit. The second part of the ratio detector is considered as the load on the tuned tank circuit. This load consists of all the other components connected to the tuned tank circuit, such as the diodes, resistors, and capacitors. The amount of load determines the bandwidth the ratio detector will respond to. The first thing you probably noticed about this circuit is that diodes D4 and D5 only allow current to flow in one direction through the load. The three resistors, R12, R13, and R14, make up a voltage divider. The other thing you probably noticed was the dual capacitor arrangement bridged across resistor R13. Capacitor C19 simply stores any electrical imbalance produced by a swing in input signal. Capacitor C20 looks at the total input power across resistor R13 and is charged to its average level. Capacitor C20 therefore acts to absorb variations in amplitude which would otherwise cause audio distortion. This feature allows the ratio detector to be used without a limiter circuit preceding its input. Now let's examine how this circuit operates. When the input frequency is exactly 4.5 MHz, the load portion of the circuit will have a balanced condition. That is, the capacitive and inductive reactances will be equal, and only the resistors will have any effect on the current flow through the circuit. When the input frequency swings below the 4.5 MHz tuned frequency, the load portion of the circuit will see more capacitive reactance than inductive reactance. The detector circuit will therefore be thrown out of balance. More capacitive reactance than inductive reactance means the current in the circuit will be pulled higher because the reaction of the circuit is that of a capacitor. A discharged capacitor, when connected to a battery, will cause a current surge in the circuit. The current surge is due to the capacitor's need to charge to the battery's voltage potential. Since there is a pool of current to charge the capacitor, the voltage level will start out very low and build up as less current is required to fill the capacitor's charge capacity. This trade-off of current to voltage always occurs in charging capacitors and circuits with capacitive reactance characteristics. As you can now see, when the input signal swings below the 4.5 MHz tuned frequency, the ratio detector will react capacitively, and the voltage will drop, whereas the current level will be high. Just the opposite is true when the input signal swings above the 4.5 MHz tuned frequency. When the input signal swings higher in frequency than the 4.5 MHz tuned center frequency of the circuit, the inductive reactance will overtake the capacitive reactance. The detector will again be thrown out of balance, but in the opposite direction. The inductive reactance overtaking the capacitive reactance means the circuit reacts to the change in frequency the way a coil reacts when a battery is placed across its leads. When a battery is first connected to a coil, the coil will initially oppose any change of current through it. As the current is building up through the coil, the voltage starts out quite high and gradually lowers as the current increases. As the magnetic field becomes saturated, the current will continue to flow, and the magnetic field will remain at saturation. It is now easy to understand how a frequency increase in the input signal can cause the circuit to react inductively and provide a higher voltage to the output. When the ratio detector is in operation, the frequency modulation of the 4.5 MHz input signal will cause the reactances to change as the frequency deviates back and forth. Now, let's finish off the ratio detector by examining the de-emphasis section of the circuit. Resistor R15 and capacitor C21 provide de-emphasis to the higher frequency audio signals. De-emphasis is needed in the television receiver because the TV station pre-emphasizes the higher audio frequencies, so noise will not be present. Therefore, the television receiver must de-emphasize the audio signal to the normal level. The ratio detector provides a variable DC voltage to the audio output based upon the frequency deviation of the RF input signal. At this point, we will pause for a review of the material just discussed. The tuned tank circuit is the heart of the FM ratio detector. Without the tuned tank circuit, the ratio detector would not respond properly to the changing input signal. A tuned circuit is affected by the input signal in one of three ways. 1. The input signal is exactly 4.5 MHz and the circuit is electrically balanced. In this condition, no audio output is present. 2. The input signal is below the tuned frequency of the tank circuit. In this case, the circuit reacts like a capacitor and draws a heavier current, which results in a lower voltage appearing at the audio output. And 3. The input signal is above the tuned frequency of the tank circuit. When this occurs, the circuit reacts like a coil and opposes any initial change in current. A low current means a higher than normal voltage for the audio output. The ratio detector outputs a variable DC voltage based on the frequency deviation of the input signal. The normal audio output level of a ratio detector is half the level expected with other FM detector circuits. This is because the ratio detector only rectifies or uses half of the incoming RF signal. This concludes review number 4. Now stop the video and complete section D in your student workbook. In this portion of the video, you will learn about stereo TV, or more exactly, multi-channel television sound, or MTS. On March 29, 1984, the Broadcast Television Systems Committee, or BTSC, established guidelines for MTS. Multi-channel television sound not only includes provisions for stereo television, but also paves the way for a secondary audio program, or SAP channel, which may also be used to broadcast a program in an additional language. MTS also makes provisions for what is termed a professional channel. The professional channel makes possible the transmission of other information not necessarily related to the main TV broadcast. The professional channel could be used for basically anything, such as voice communication from television station to live news crews, or the transmission of digital data for scrambling the picture of the TV channel, or digitally setting a particular mode of operation within your television set. There can be more than one professional channel per TV channel, as long as bandwidth is available. It was mentioned previously that the RO carrier has a deviation of plus minus 25 kHz and that it was spaced 4.5 MHz from the visual carrier. With the visual modulation taking up to 4.2 MHz of bandwidth, this left a 275 kHz guard band between the visual modulation and the RO modulation. When MTS is used, the FCC allows the RO carrier to deviate no further than plus minus 75 kHz to accommodate the entire audio baseband. With the addition of MTS modulation on the RO carrier, the audio baseband will now extend from 50 Hz to 120 kHz. Now, let's examine the audio output of the sound detector stage. In addition to the main audio channel, this audio output contains the MTS audio subchannels when de-emphasis is not used in the sound detector circuit. De-emphasis would roll off the higher MTS subchannel frequencies. However, de-emphasis is used later in the stereo television receiver. The main audio channel is the first position on the audio baseband of frequencies. The main channel has audio frequencies ranging from 50 Hz to 15,000 Hz. When stereo multiplex is used, the main audio channel is a combination of both left and right audio soundtracks. This is done so a television receiver not equipped with stereo decoding may reproduce the entire audio content of the program, although without the stereo separation. With a stereo transmission, the main audio channel may now be referred to as the stereo sum, or the L plus R signal. The next item on the audio baseband is the pilot tone, located at 15,734 Hz. This pilot frequency is protected by the FCC for use with the BTSC stereo decoding method. When a television receiver equipped with stereo decoding detects the 15.734 kHz pilot signal, the stereo circuitry will be activated and BTSC stereo decoding will be enabled. When using the BTSC system, the pilot tone may deviate plus minus 2 Hz in frequency. You may have noticed that the 15,734 Hz pilot frequency is the same as the horizontal sync frequency. When a stereophonic broadcast is transmitted, the pilot tone is locked to the picture's horizontal sync pulse to minimize any beat or buzz which can occur between the picture and sound carriers. Information regarding the horizontal sync pulse will be covered in the next You Can Do TV video. The stereo difference, or the L-R signal, has an audio bandwidth of 50 to 15,000 Hz, the same as the L plus R signal. The L-R signal is centered around an AM double sideband suppressed carrier of 31.468 kHz. The 31.468 kHz subcarrier is twice the frequency of the pilot tone, or horizontal sync frequency. As you can see, the stereo television baseband of MTS resembles the stereo baseband used in FM radio broadcast. Now let's examine how stereo television is decoded. Here you see a block diagram of the process in which stereo television is decoded. The multiplexed audio arrives from the sound detector stage and enters the SAP trap. This sound trap is tuned to notch out ultrasonic frequencies centered around 78.67 kHz. The stereo decoder receives the multiplexed audio which is passed to it from the SAP trap. The stereo decoder uses the pilot signal to separate the L plus R and L minus R audio signals. When a stereo transmission is being received, the stereo decoder will turn on the stereo indicator LED. The L plus R audio signal goes through a low-pass audio filter. The L plus R audio signal then goes to the matrix decoder stage. The L minus R audio signal goes to the noise reduction stage. The noise reduction stage expands the L minus R signal to its original form prior to noise reduction at the transmitter. The L-R audio signal now goes to the matrix decoder, where it is combined with the L+R audio signal. The matrix decoder separates the L+R and L-R audio signals into individual left and right audio channels. Now let's take a look at the circuitry associated with each of these stages. The multiplexed audio arrives from the sound detector stage and is passed to the SAP trap. As you can see, the SAP trap is a simple parallel-tuned resonant tank circuit. This trap responds to ultrasonic frequencies around 78 kHz and passes the remaining frequencies to the next stage. The stereo decoder is made up of 4 integrated circuits, the first of which is IC1, a low-power op-amp. IC1 acts as a buffer to isolate the output of the sound detector with the stereo decoding circuitry and to provide a low impedance source for driving IC2. IC2 is a stereo demodulator. The stereo demodulator takes the buffered output of IC1 and detects the L+R and individual left and right audio signals when the pilot signal is present. This is accomplished by a phase-locked loop built into IC2, which locks to the 15.734 kHz pilot tone. Most stereo television receivers are equipped with a frequency adjustment to precisely set the phase-locked loop on the stereo pilot frequency. In this example, the frequency adjustment is made by a variable resistor. IC3 is an op-amp which receives the individual left and right audio signals from IC2. IC3 recombines both left and right audio signals through its differential inputs. This is done primarily for the purpose of additional audio processing to the L-R difference signal in the noise reduction stage of the stereo television receiver. IC4 is an op-amp circuit used as a low-pass filter for the L-R difference signal. A low-pass filter is required to roll off the higher frequencies so that they won't overmodulate and distort during the noise reduction process. The L-R signal now goes to the noise reduction stage. Transistor Q1, which receives the L-R signal from IC4, is a PNP RF-IF silicon transistor. Transistor Q1 provides 3 functions to the L-R signal: to control the audio level into the noise reduction stage, to provide a low impedance source to drive the next circuits, and to provide inversion of the L-R signal to offset the expander's reverse output polarity. A 75 microsecond de-emphasis circuit is provided after transistor Q1 by resistor R27 and capacitor C36. De-emphasis is needed because of the pre-emphasis at the transmitter. Here you see a chart showing the effect de-emphasis has on frequency versus audio level. This chart is plotted using a logarithm of frequency. Here you see the same data, but depicted with an equal frequency distribution. Noise reduction is used because the L-R signal contains more noise having been transmitted on the higher frequency spectrum of the audio baseband, even after the 75 microsecond de-emphasis. To reduce this noise even further, a method of companding is used. Companding is actually made up of 2 words, compressing and expanding. Prior to the L-R signal being transmitted, the signal is compressed. After the L-R signal is received by the television and demodulated, the signal is expanded or brought to the condition it was in before it was compressed. In this manner, the frequency content of the transmitted modulation will overcome the frequency response characteristics of the transmitter, and a better signal-to-noise ratio will be achieved with the L-R signal. The L-R signal splits from transistor Q1 and goes to transistor Q2 and IC5. Transistor Q2 reinverts the L-R signal for one of the inputs of IC6. IC5 provides a high-pass filter for the other input of IC6. This high-pass filter helps to eliminate any vertical sync buzz which may be present in the L-R audio signal. IC6 is used as a 2-to-1 audio expander for the L-R signal. IC6 simply doubles the amplitude of the L-R signal based on its frequency content. At the output of IC6 is another de-emphasis network. However, the delay of this de-emphasis network is 390 microseconds. This timing constant is standard with the BTSC television stereo system. The L-R signal leaves the 390 microsecond de-emphasis network and travels to IC7. Since the L-R signal has been expanded, a high-pass filter is used again to take out any low-frequency components which were expanded in the L-R signal by IC6. The L-R signal is now passed to the matrix decoder. The L+R signal leaves the stereo decoder and is passed to a low-pass filter. IC8 is an op-amp circuit designed for low-pass operation just like IC4. Right after IC8 is a 75 microsecond de-emphasis circuit exactly like the one used for the L-R section. The de-emphasized L+R signal is then passed through transistor Q3 to the next stage within the stereo television receiver. The next stage the L+R and L-R signals go to is the matrix decoder stage. As you may recall in FM Radio Part 2, the same basic process which encoded the L+R and L-R audio signals may also be used to decode the L+R and L-R audio signals into individual left and right audio channels. The L+R signal comes from the low-pass filter and enters potentiometer R1, while at the same time the L-R signal comes from the noise reduction stage and enters potentiometer R2. Both R1 and R2 control the input level to the matrix decoder. Both L+R and L-R signals go to IC9 and IC10, which are two op-amps. The L+R signal goes to the inverting input on IC9 and IC10. The L-R signal goes to the non-inverting input on IC9 and the inverting input on IC10. IC9 functions to isolate the right audio channel, while IC10 isolates the left audio channel. We will now pause for a review of the material just discussed. The letters MTS stand for multi-channel television sound. Multi-channel television sound encompasses stereo, SAP, and one or more professional channels. In order for MTS to be used, the sound detector must not contain a de-emphasis circuit. De-emphasis is used just before the matrix decoder. The SAP trap simply filters out the secondary audio program subcarrier prior to stereo demodulation. When a stereo broadcast is transmitted, the stereo decoder extracts the stereo information from the MTS audio and provides separate left and right outputs and a composite L+R signal. Most stereo decoders will activate a stereo indicator to advise you that the program is in stereo. The noise reduction stage takes the L-R signal and removes the noise while providing de-emphasis at 390 microseconds. A low-pass filter is used on the L+R signal to roll off the higher frequencies. The matrix decoder simply separates the L+R and L-R signals into their individual left and right channels. This concludes review number 5. Now stop the video and complete section E in your student workbook. Many color television receivers are capable of receiving a secondary audio program or SAP channel. When the SAP audio mode is selected, you may hear your favorite television program in a different language instead of the one you are accustomed to hearing. When a secondary audio program is being transmitted, the main sound detector will contain the SAP information on its audio baseband. The secondary audio program is frequency modulated and is placed at 78.67 kHz on the main audio baseband. The same compression method which is used on the L-R signal is also used with the SAP signal. Here you see a simple block diagram of an SAP audio section located in a color television receiver. The first stage is the SAP bandpass filter. The SAP bandpass filter only allows the 78.67 kHz secondary audio program to pass through to the next 2 stages, while stopping all other frequencies. The carrier detect stage looks for the presence of the SAP signal. When the SAP signal is present, an LED will indicate that a secondary audio program is being received. The SAP decoder demodulates the frequency-modulated secondary audio program information into a low-level audio signal. In most television receivers, the low-level secondary audio signal will use the same noise reduction stage that the L-R signal uses. Therefore, a set of switches will route low-level audio from either the L-R or SAP signals into and out of the noise reduction stage. After the noise reduction stage, the SAP audio bypasses the matrix decoder stage and goes directly to a mono stereo switch. The mono stereo switch electrically connects both left and right channels when the main audio program is not in stereo or when the SAP audio mode is selected. The low-level audio output leaves the audio switch and is passed into the last stage of the television sound strip. The professional channel, when used, is normally placed on the television audio baseband at 6.5 times the horizontal sync frequency, or 102.271 kHz. The professional channel is designed for use by the television broadcaster. When audio is placed over the professional channel, the subcarrier will be in the form of narrowband FM, and the demodulated audio frequency will range from 0 to 3.4 kHz. A 150 microsecond de-emphasis is required to restore the proper characteristics to the audio. When data is transmitted via the professional channel, frequency shift keying will be used with an audio frequency range of 0 to 1.5 kHz. No de-emphasis is needed when data is transmitted over the professional channel. When more than one professional channel is used on the main audio baseband, only the subcarrier frequencies change. The last stage in the sound strip of the color television receiver is the audio amplifier stage, or stages if the television is equipped for stereo reception. Let's examine a simple audio amplifier circuit. Here you see a simple 2-transistor audio amplifier circuit. When the television receiver is stereo, there will be one amplifier circuit for each of the left and right audio channels. A volume control is provided by resistor R1 to vary the input to the audio amplifier stage. Capacitor C1 couples the low-level audio into the first transistor stage. Resistors R2, R3, and R4 provide the base bias for transistor Q1. Resistor R3 also controls the gain of transistor Q1. Transistor Q1 is basically used as a driver or preamp for transistor Q2. Transistor Q1 variably pulls down the control line going to transistor Q2 according to the audio modulation impressed upon Q1's base. Transistor Q1 is of course direct coupled to transistor Q2. Resistors R5 and R6 limit the amount of current available to transistor Q1's output. Capacitor C2 is used to maintain a level voltage for the output of transistor Q1. Transistor Q2 is the final power amplifier stage. Transistor Q2 controls the power flow to the speaker system. Resistor R7 is the emitter limiting resistor. Capacitor C3 is used to bypass any voltage ripple to ground. Capacitor C4 functions to store up power for current surges when transistor Q2 conducts heavily. Audio transformer T3 magnetically couples the audio signal to the speaker system. Transformer T3 also provides the proper impedance match so the most power can be transferred to the speaker system with the least amount of loss. At this time, we will pause for a review of the material just discussed. The letters SAP stand for Secondary Audio Program. The SAP audio subcarrier exists on the main audio baseband at 78.670 kHz. The demodulated SAP audio is compressed like the L-R audio signal, and in most television receivers, we use the same noise reduction stage to expand both audio signals. The professional audio channel is used by the broadcaster for either voice or data communication. When audio modulates the professional channel, the audio frequency range will be from 0 to 3.4 kHz. A 150 microsecond de-emphasis is required when audio is used. When data is transmitted over the professional channel, frequency shift keying will be used to transmit digital information over an audio range of 0 to 1.5 kHz. When the television is stereo, there will be two identical audio amplifiers for the left and right audio channels. This concludes review number 6. Now stop the video and complete section F in your student workbook. Every good technician needs to understand the theory and concepts behind today's modern technology. Study and review your You Can Do videos often to gain the most from them.